Welcome to another video on ABC, another basics of circuits. We shall continue the IV characteristics of most important semiconductor devices, that is BJT and MOSFET. The previous video we have already seen the simulation of BJT IV characteristics. All the three input IV characteristics, transfer IV characteristics, as well as the output IV characteristics. So in this video we will concentrate on the MOSFETs. Okay, these are the now with this input, let us move on to IV characteristics of this MOSFET. You can see there is a major change in this circuit connection of a BJT IV characteristics and MOSFET IV characteristics. So if I write one after the other, suppose if I write it for BJT, it comes with this. So this was actually written as VCC, and this was VBB, and this was actually VBE, and this was RB, and this was RC, and this is plus minus VCE, this is VCC. Now the major difference you can see is there is a resistor here at the base and there is no resistor here. There is a resistor at the collector, there is no resistor at the drain. Of course we know that this is gate, this is drain, this is source of the MOSFET, and we will also have a bulk connection which will be available, that will be usually connected to source potential. So this is bulk. So this is a four terminal MOSFET, where we have exclusively we need to make four terminal connection for gate, drain, bulk, and the source. So why this RB is there? Because this is a current control device. This is current controlled device. This is a voltage control device. Voltage controlled device. If you don't use IB here, so then when IB is 0, you're going to have a huge current flowing through this. So when you don't have a resistor RB, this IB will be very large, which will make a lot of IC to flow through the transistor, and then this transistor may get damaged if the current exceeds the rated current of this. Coming to this, since the gate current of a MOSFET is 0, so that is, since there is an insulator at the gate, since IG is 0, there is no need to have any resistor over here. So since the impedance is infinity, there is no current going into the gate at all. Of course, we have the expression for the drain current as given by. So of course, we will write the IV characteristics of this MOSFET. It has got only two characteristics, that is, so it has got a IV characteristics. One is the transfer characteristics, which refers to the variation of VGS and its effect on the drain current. So there is no IG, so that's why we have only the transfer characteristics. So it will going to have some threshold voltage VTO or VTH, and till that point it will be of zero current. Afterwards it increases quadratically. Again, this is for a particular value of VDS1. If you increase VDS to a different value, of course it will be slightly away from this. This is VDS2. It's not too far away from each other, so they'll be very close to each other. This is transfer characteristics, IV transfer characteristics. So next we have this is for the MOSFET. This is n-MOSFET. Next we have output IV characteristics. Output IV characteristics. So since it is output characteristics, we are dealing with VDS, that is the output voltage, and the output current ID. It is going to have the characteristics something like this. This is for different values of, so you can see now here it is becoming constant, from here it's becoming constant, from here it's becoming constant. This is VGS1, VGS2, this is VGS3, and I have written these lines 1, 2, 3 lines indicating that after which the current almost becomes constant. Can you see the current is becoming constant here? This we'll call it as VDS SAT1, this is VDS SAT2, VDS SAT2. SAT is actually saturation. The meaning of SAT is saturation. It's a short form of representing this. This is zero voltage and zero current. So this is that origin. So now, as we saw in BJT also, till V gamma this was not conducting, so which is typically 0.6, 0.55, and it's around that voltage. And here also we have similar to that VTH, we want to have a VTO or VTH, which we call it as the threshold voltage. Threshold voltage. That is, if the gate to source voltage is not exceeding the threshold voltage VTH, then the MOSFET is off. So if this MOSFET has to turn on, then VGS has to be greater than V threshold voltage. So then only it turns on. You can see this is, here it is off, here it is on, here it is on. So that is, anything after this it is on. This is on, this is off. So once it is on, so now you can see here all these VGSs are greater than threshold voltage, and once it is on, the current varies quadratically. The current varies quadratically, whereas here it was varying exponentially. The increment is too much when compared to, suppose if I compare this and the MOSFET 1 will be slightly lower, whereas this is sharper. This is exponential because e power x is far greater compared to something like x square. So this is square, this is e power x. Okay, that's how it is changing. So now this is what is the transfer characteristics and output characteristics of this n MOSFET. So now this MOSFET drain current equation, this is my drain current ID, which is going into the drain to source. So this current flows from drain to source. So now, depending on the region of operation, you can see here we have the output characteristics. Here you can see for a certain value of VGS, the current initially increases linearly and then it almost becomes saturation. So as the region is varying like this, okay, it is linearly varying, so we call it as linear region. This is linear region, or sometimes called as triode region. Triode region. So this region where it is increasing along with this VDS, it is called as linear region or triode region. And where it fairly becomes constant, you can see it's almost constant here, it's almost constant here, it's almost constant here. This, since the drain current is saturated, we call these regions as saturation region. Saturation region. This, all the three are saturation regions for a given VGS. Very interesting to observe the major difference between the BJT and the MOSFET characteristics is here this, where it becomes constant is varying, but here you can see they're almost becoming constant at the same time. So they become constant at the same point. And here the difference is this is said to be active region and this is said to be saturation region. And here, of course, don't get confused with the saturation region of this BJT and the MOSFET here. We specify the saturation region of BJT as when both emitter base junction and collector base junction are forward biased. So this is when both the junctions are forward biased. Here emitter base junction is forward biased and collector base junction is reverse biased. So that's what is active region. So since you have two junctions, so we talk about collector base junction and emitter base junction. Whereas in case of MOSFET, it is totally different. Why it is said as saturation is, we know that the English dictionary meaning of saturation is becoming constant. Can you see, is this becoming constant? That okay, that reason or that meaning applies here. Here it becomes constant. Now the question is, when it is becoming constant? It becomes constant at different VDSs. That's what is known as VDS SAT1, VDS SAT2, VDS SAT3. These saturation voltages certainly depends on the applied VGS and the V threshold voltage. Meaning the voltage at which this becomes saturation, the saturation region starts depends on VGS and VTH. Meaning, so as I said, this is linear region, this is saturation region. For saturation region, one thing is VGS has to be greater than VTH. First it has to turn on. So there is no question, if it is not turning on, there is no point. Then most importantly, VDS, that is, what is this voltage? This should be greater than VDS SAT. So what is this VDS SAT? VDS saturation is given by VGS minus VTH. So let us take up an example. So this is the voltage which we say the MOSFET is in saturation region, provided if the VDS is greater than VDS SAT. How do you find VDS SAT? It is VGS minus VTH. So let us take an example. So assume that VTH of a transistor is 0.4 volt. So let me just take this example. So this is the example what I have. So now let me take it as 0.6 volt, and this is, assume that this is 1.2 volt. So now what is VDS? Sorry, what is VGS first? VGS is 0.6 volt. This is certainly greater than VTH, which is 0.4 volt. So MOSFET is on. Once it is on, find out what is VDS. What is VDS? VDS is 1.2 volt. This is the thing that is applied across this. VDS is 2 volt. So now for this VGS, how much is VDS SAT? VDS SAT is VGS minus VTH. How much is VGS? It is 0.6. How much is VTH? 0.4. It is 0.2. So what is this? This is VDS SAT. What does this VDS SAT actually mean now? Suppose if this is 0.6, for a voltage of VDS around 0.2, so from here this becomes constant. So now how much is the VDS you have? VDS you have it as 1.2 volt. Is this 1.2 volt greater than 0.2? So now when VDS is 1.2 volt, which is far more than, now what is the condition? VDS is greater than VDS SAT. Why? Because we know that 1.2 is greater than 0.2. So what is the region of operation? MOSFET is on because VGS is greater than VTH, and VDS is greater than 0.2. VDS is greater than VDS SAT. So since these two conditions are satisfied, the MOSFET is in saturation region. This is in saturation region. So let us suppose if this voltage goes to 1 volt. If this voltage goes to 1 volt, suppose if this voltage goes to 0.8. So what is the region of operation? So VGS now equal to 1 volt, VTH is 0.4. From these two comparison, I can say VGS is greater than VTH, so it is on. Correct? So what is VDS sat for this threshold voltage? For this VGS, it is VGS minus VTH, which is 1 minus 0.4, which is 0.6, which is 0.6. How much is VDS? VDS is 0.8. 0.8. Is 0.8 more than 0.6? Yes. So this is also in saturation. Assume that I make it 0.2 volt. So now, how much is VDS? VDS is 0.2. How much is VDS at? This is 0. I'm not changing this. So let this be 1 volt. 1 minus 0.4 is 0.6. So now 0.6 is less than 0.2 volt. So that system is in linear region. That means you have applied 1 volt, but VDS is how much? 0.2 volts. So it's in linear. Can you see this is in linear region? Because this is here and your VDS is here. Suppose you make it maybe 1 volt. If you make it 1 volt here, then it comes to saturation. Fine. This is about region of operation of the MOSFET, whether it is in linear region, saturation region, or cutoff region. So let us try to uh, get the equation for the current in 3 different regions. So let us write the equation. Since diode is off in cutoff region, where VGS is less than or equal to VTH, even if it is equal to, it is off. So then ID is 0. Now in case of linear region, where VGS is greater than VTH, but VDS is less than or equal to VDS sat. So then ID expression is half mu n Cox W by L to VGS minus VTH into VDS minus VDS square. This is the expression for the drain current in linear region. You can see now, since it depends on VDS, so that's why it is, if you can see here, suppose if you're if I just go to this, can you see if in this region, if your VDS changes, can your drain current is changing? This is increasing as your VDS increases. That's why in this expression of ID you have a VDS along with these parameters. So this mobility of the electrons, and this is the gate oxide capacitance, the dimension of the device, width and the length. VGS is the gate to source voltage, threshold voltage, and VDS is drain to source voltage. Then you have the another region called as saturation region. In this saturation region, VGS has to be greater than VTH. It has to turn on. Then VDS should be greater than VDS sat. So let me also say what is VDS sat. VDS sat is equal to VGS minus VTH. So expression of ID in saturation region is half into mu n Cox W by L into VGS minus VTO or VTH whole square. This is not having VDS term at all. It is half into mu n Cox W by L into VGS minus VTH whole square. So as you can see here, in saturation region, current is quadratically varying with VGS. So that's why we had this. Can you see here? We had this. So this is almost quadratically changing. And since ID is independent of VDS in saturation region, so that's what is. So from here to here, whatever the value of VDS changes, current is not changing, because in this expression there is no VDS at all. There is no VDS at all. Okay, now we shall do a design for a particular value of. Let me just take. Okay, this is. Okay, this is page number 3. This is 3, this is 4, and this is 5. So let me take the dimension of the device and the other parameters. Okay, this, so whatever UNC of we just mentioned, so this is also set to be KP, the kappa of the device. So this is one of the foundry defined parameter, so that is not in the users or the designer's hand. KP is equal to, usually taken as 200 microampere per volt square. This is the typical value of KP in most of our circuits. KP stands for mu n Cox. So this is mu n Cox. So sometimes we write as KP of n. So similarly for PMOS transistor, you write mu P Cox, which will be KPP, which will be usually 100 microampere per volt square. This is for PMOS transistors. Since we are dealing with n-MOS transistor, Kp of n is this much. So let us assume that VTO is equal to 0.4 volt. And let us assume that length of the transistor be 1 micrometer. So let us assume that width is around 50 micrometer. So W by L will then become 50. It is 50 micrometer divided by 1 micrometer, which will become 50. So let us take a VGS of 0.6 volts. Let us keep a VDS of maybe 0.1 volt once, and maybe let us keep this at 0.8. Let us keep this at 0.1, and if you want to get this characteristics, so what I have to do in my circuit, I had to keep this at maybe some 1 volt and sweep this. So in order to happen this, I need to define the system parameters as these. So these are my system parameters. So these are model parameters. So let us go to simulation and then start. Let me take this new sheet. Okay, let me take, it's already there. Okay, so now let me add n-MOS4. So you can see there is a n-MOS4. As I said, this is gate. Nearer to gate is this is gate, and nearer to gate is source. This is bulk, and this is drain. Let me take a voltage source here. I can connect one more here. That's it. And then rest is, I want to have a ground. You can put ground somewhere here. Then I will do the connection. Do this. For doing the connection, this is the wire. You can start making the connection. This all the way down here. Then you can start from here. This goes. Okay, let me minimize, fit this. You can see now. Okay, I can run here. This is going all the way, and then this is connected to this. Then I can make this view fit. This is connected to ground. Since sources are connected, this is like, okay, bulk and source are connected to ground, and I need to put the model parameters. That's where here this is dot model n-MOS nMOS, open the parenthesis and then say it as Kp is equal to 200 micro, comma VTO is equal to 0.4. VTO, we have to write VTH is not allowed here. This is the model parameter. I will specify the dimensions here. So length is 1 micro and width is 50 micro. So how to edit the dimension? Just right click on the device. On the device, you'll get this window, and then here you can edit. And maybe you can just give some 1 volt here. Give this as maybe another 1 volt, and you can sweep. Of course, you can make this sure that this is 2 volt. And since it's a variable, okay, let us vary this in DC sweep. This is my DC sweep. The source I want to change is V1. The source type is linear. I will start from 0 up to maybe 1 volt in steps of 10 millivolt. That's it. So I'm done with my specifications. Do this. Now the moment I run, I'll get this. This is VGS, because this is varied from 0 to 1, because no need to again label this as VGS. V1 itself is VGS. Next I want to plot the current. So plot the current means you can come over here and add the trace. You can see you can add the trace. Trace is nothing but ID of M1. You can say this is, can you see it's almost 0.4. It is current is 0, from then it is increasing. This is how it is increasing. This is transfer characteristics, correct? Because we are relating ID and VGS, ID and VGS. Suppose if you want to do it for different voltages, you can certainly do. How do you do? So just go here. Again, this is V2. Make it as a list value. Make it as 2 volt, maybe 4 volt, maybe 6 volts. So these are all, you'll get 3 plots. They'll be almost, let us see, they'll be almost overlapping. You can see they are almost overlapping. You cannot differentiate. So as we saw the same type of get transfer characteristics in case of BJT also. So as I just mentioned here, so there is no much difference, VDS1, VDS2. So you'll almost see on top of that. Fine. This is transfer characteristics of MOSFET with a dimension of 50. And then let us do the output characteristics, for which this will be V1 second sweep. Let me give it as maybe 0.8 is first sweep, make it 1 volt and make it 1.2 volt. And the first source is actually V2. You can vary from 0 to maybe 5 volts in steps of 10 millivolt. So what you'll get is, you will get for 3 different values of VGS. So you'll actually get, as I mentioned here, you'll get it for VGS of maybe 0.6, 0.8 or 1. So whatever values that I put, I'll get 3 graphs. Okay, let me go back here and then save it and run. See there, don't you have these 3 plots? This is for a VGS of 0.8 volt. This is for VGS of 1 volt. This is for VGS of 1.2 volt. You can actually verify the currents here. So you have a current of almost 800 800 microampere. Let me just list the values. For one of them, ID is 800 microampere. For the next, it is let me just redo it again. There is 1.8 milliampere, and next one is 3.19 milliampere. So there are three currents corresponding to it. So that's in saturation region. Let us go back to this. So these are the three currents. So what we have, the expression for ID in saturation region is half that Kp of n into W by L VGS minus VTO whole square. So let me just verify. So VGS, okay, this is half into 200 micro into 50 into VGS is keep changing from zero 0.8, 0.4 whole square. This is 0.8 once, 1 once, 1.2 once. So let me do that. It is 0.5 into 200 exponential minus 6 into 50 into, let me make it as a variable, alpha a minus 0.4 whole square, sorry, whole square, calculate for 0.8. I got a current of 800 micro. So this is my 800 micro. This is my calculated value. Then I will do it for 1 volt. It's 1.8 milliamperes. Can you see this is 1.8 milliamperes? So this is my simulated value. Calculate for 1.2 volt. Can you see it is 3.2 milliamperes, which is 3.19 milliampere simulation. You're getting it as almost same. So these are all what? The currents in saturation region, meaning VDS is certainly greater than VDS sat. So what is VDS sat for this? It is 0.4. VDS sat for this is 0.6. VDS sat for this is 0.8 volts. So you should keep the value of VDS more than VDS sat, then this current will be correct. You can also see that when it is becoming saturation, can you see this saturation voltages are differing? It is saturating here and it is saturating here and it is saturating here. The saturation voltages are different. Okay, if I just zoom this, you can make it much more clear. Wait just a minute. I'll properly zoom it so that you can able to make out. I will just zoom this portion. Okay, now let me zoom it here. See, here it is becoming constant, here it is becoming constant, it's becoming constant here. Meaning it's not becoming constant at the same voltage, it's becoming constant at different voltages. Oh, sorry. It is better here.
ಅದು ಮಲ್ಟಿ ಸ್ಟ್ರಾಕ್ಟ್ ಆಗಲ್ಲ ಸರ್, ಅದು ಲೆಡ್ ಕೂತ್ಕೊಳ್ಳಲ್ಲ.
Okay, this is how it's that VD sat is keep changing. If you can actually notice, this only one cursor. Here VGS is 0.8. At around 0.4 it becomes constant. Can you see this is around 0.4? It is becoming constant. You can see here it is constant somewhere here. This is 0.4. Almost you are there at 800 micro. And this is becoming at around 0.6 volts. So it's around. So what is the current? The current is 1.8. Okay, let me just go to next. Okay, now it's not yet constant here, so it's almost here somewhere here. So at 0.6 it is becoming constant. Next it becomes constant after a VDS of 0.8 volts. Can you see here it is almost 3.2. So you can see this is almost 800, meaning VDS sat changes with, what is VDS sat for this? We had VGS is equal to 0.8, 1 and 1.2. The corresponding VDS sat is VGS minus VTH, that is 0.4, 0.6, 0.8. These are the VDS sat. Okay, this way we can able to do the simulation and understand the working of the MOSFET in three different regions. How to ensure that you have the current for, you'll also verify the site cutoff region. For cutoff region, what to do is make one of the voltage. Okay, let me just show you that. Let me make uh, this list now. This list, let me make one voltage which may be 0.4 itself. 0.4 itself. So for 0.4, the MOSFET is off. See here, this is off. What is the current? You can see the current. Current is 5 picoamperes. This bottom one. Pico means 10 to minus 4. The MOSFET is off. Next current you can see it is 1.8. So this is okay. First one is zero point 0.4. Next one is 1 volt. For 1 volt you got 1.8 milliamperes. That's what is there. Correct. For MOSFET to turn on, you have to have a voltage more than VTH. Not equal to VTH is also not correct. You need to have more than VTH. Hope okay you got the equations being verified. Okay, let us verify one value for the linear current. So this is moving on which curve? Okay, this is moving on the second curve. So let us know what is the value of VDS. So how much is VDS? It is 189.9 millivolt, and the corresponding ID is 959 microampere. We know that VGS is equal to I think second one is 1 volt. Second one is 1 volt. Okay, with these specifications, I'll show you. With VGS as 1, so this is VDS. I should get an idea of this much. So I have to use which equation? I have to use the linear equation. So why it's a linear equation? Because it's operating in linear region. For 1 volt, VDS at is 0.6. So this is 189 millivolts, less than 600 millivolts. So it's in linear region. I have to use this equation. So now as per this, it is 100 exponent minus 6 into 50 into, open the parenthesis, 2 into, this is how much is VGS? It is 1 minus 0.4 into VDS is, how much is VDS? It is 0.189 minus of 0.189 square, close. You can see how much is the current. The current is 955 microampere. How much was the current? You can see you have 959. So using calculation, we are getting a current of 955 microampere. In simulation, I got 959 milliampere, microampere, hardly 4 microampere difference from equation to simulation. This is almost, so this is in linear region. For linear region, I have to use this equation. Half Kp W L 2 whole into 2 VGS minus VTH into VDS also. So this is the equation what I have. See, this is 200 into half, which is 150. Then it is, then you can see this is 2 into 1 minus 0.4 into 0.18 minus 0.189 whole square. Okay, 2 into VGS minus VTH into VDS minus VDS whole square. So that current is 955 micron. Thank you. Repeat this for different values of dimensions and device voltages.